What's going on, everyone? Welcome back to my YouTube channel. It's Max, and today I wanted to talk about a problem that popped in my head a few weeks back. And at first, when I started thinking about this problem, I didn't really think too much of it. I thought it would be a simple problem and it would, I'd figure it out pretty quickly. But the deeper I dug into it, the more complicated and interesting it became, and the more I thought it could be a good topic for a YouTube video. So the topic falls into the area of probability. And probability is one of these subjects that can be very difficult for people, and it's very easy for people to misuse and misunderstand the tools. And I think there's two main reasons for this. One is the subject itself is just inherently a difficult subject with lots of math. And two, a lot of the results that come out of this subject can drastically disagree with our initial intuition about an idea. Let's take the famous birthday problem as an example. So the birthday problem goes something like this. Suppose you have a room full of people. The question is, how many people do you need to be in that room for there to be a 50% chance that at least two people in the room share the same birthday? For simplicity, we're not going to take into account things like leap years or like identical twins or anything like that. There's just going to be people in a room. They can have one of 365 unique birthdays, and all of those birthdays are equally likely to happen. Seems reasonable enough, right? If you ask someone who hasn't seen this problem before, their line of reasoning usually follows a path like this. First, they reason about simple cases that they can easily find the answers to. One example is the case of two people. Say, if person A has a birthday of March 7th, then person B will have a 1 out of 365 chance of having that same birthday, or about 0.3%. Another easy case is for 366 people. This is because you can spread the unique 365 possible birthdays among all the people, then one person will be left over and they will have to get a birthday that someone else already has. At this point, the person now has two data points. They have one point that is two people with a 0.3% chance, and 366 people with a 100% chance of sharing at least two birthdays. At this point, the natural thing our brains will do is just kind of linearly interpolate these 2 points. So the person might guess some number around the middle between 2 and 366. So let's just say like 180, like roughly about half of 365. Again, there isn't anything rigorous or exact going on. We're just talking about sort of the direction our intuition will go in. So without actually solving the entire birthday problem, let's just jump to the answer. Are you ready? So the number of people you need to have a 50% chance that any two people in the room share the same birthday is 23. And I think for most people, this number is a lot smaller than what they would guess. But why is this? Why does this answer disagree so much with our intuition? Sure, we could go through all the math and show how we end up at 23, but what's the actual intuitive explanation for what's going on here? So, sorry for the cliffhanger, but we're not going to go into why the birthday problem is the way it is. In this video, I want to focus on a problem that I've been thinking about for a while. And in several ways, it's similar to the birthday problem, but overall a lot simpler. It's a problem that I think at face value, we all feel like we have a lot of intuition on, but as we dig deeper, the results we get are going to be a little bit unexpected. I'm not sure if this problem exists or has a name or anything like that, but for now, let's just call it the 1 out of n problem. Before we get into the problem, let me ask you to think about a question. How would you explain what the phrase 1 out of 10 chance means? I think this is one of those things where it's so ingrained in our mind, it's kind of hard to explain. And a really simple way you might say is, well, that's the same thing as there's a 10% chance. But then if you try to follow up and ask, well, what does a 10% chance mean? The explanations will kind of start to get circular. Okay, what if we think about things a little differently? Let's pretend like we're in a scenario involving, say, a lottery ticket. And let's say this lottery ticket has a 1 out of 10 chance of winning. Another way we could try to answer this, what does 1 out of 10 chance mean, is we could say, okay, how many lottery tickets do we need to buy before we expect to get a winning lottery ticket? I think what most people will say is, well, we need to buy 10 before we get one lottery ticket. And I'm not trying to say that there's a right or wrong answer to this. I would have said the same thing, that we should probably get 10 lottery tickets before we expect one. However, we know that buying 10 lottery tickets that all have a 1 out of 10 chance of winning doesn't guarantee that we'll get at least one winning lottery ticket. While it may seem unlikely, I think we can all, reasonably understand the situation that we buy 10 of these lottery tickets and none of them happen to win. Now the question is, well, what's the probability that if we buy 10 of these lottery tickets that all claim to have a 1 out of 10 chance of winning, that we actually do get at least one winning lottery ticket? Is it 90% chance? 99% chance? 51% chance? What's the actual probability? I think since we all are under the assumption that we're probably going to get at least one winning ticket if we buy 10, that it's probably some value above 51%. Because if it was, we probably wouldn't guess below, because then we would say, well, we're probably not going to get a winning ticket. This question and scenario I've just described is what I'm calling the 1 out of n problem. And in this case, this is the 1 out of n problem for n equals 10. That's because we have lottery tickets that each claim to have a 1 out of 10 chance of winning, and we're talking about the probability of getting at least one winning ticket given that we bought 10. For example, the 1 out of n problem for n equals 3 would be the case of buying 3 lottery tickets that all claim to have a 1 out of 3 chance in winning. Now, to get a feel for how this problem works, let's try to solve it for the n equals 3 case. All right, let's work out how to solve the case for n equals 3. First, let's just write down the probability that we get a winning ticket or don't get a winning ticket. So the probability that we get a winning ticket is going to be 1 out of 3. And then the probability we get a losing ticket is just 2 out of 3. Now let's list all possible cases we could get for buying 3 tickets. So start with case 1, we could lose all 3, right? So we could get lose, lose, lose. Case 2 could be win, lose, lose. 3, we could get lose, win, lose. Case 4, we could get lose, lose, win. So this first one is the case where we lose every ticket. Cases 2 through 4, these are all the cases where we win, where we get exactly one winning ticket. Case 5, we could have 2 wins, win, win, lose. Case 6, we could have win, lose, win. Case 7, we could have lose, win, win. And then case 8, we could have lose, lose, lose. So these are all the ways we could buy 3 lottery tickets. We could either get all 3 of them losing. So this is, 0 wins. Here would be 1 win, exactly 1 win. Here would be exactly 2 wins. And then here would be, whoops, not lose, lose, lose. We could get win, win, win. And then this would be the case where we win all 3 of our tickets. Oops. Okay, so now if we want to figure out what's the probability that we get at least one winning ticket, we just need to compute the probability for every single case that has at least one winning ticket and then just add them up. The probability for, let's just go to case 2, we're going to make the assumption that each lottery ticket is independent. So if I get a winning ticket for my first ticket, that's not going to influence the probabilities for the second and third ticket and whatever other combinations you want to arrange that in. And I think that's a pretty reasonable assumption. And since we can assume these events are independent, we can just multiply the probabilities to describe the probability of the entire event itself. So the probability for case 2, where we have 1 win followed by 2 losses, would be 1/3 times 2/3 times 2/3. Then for case 3, we would have 2/3 because we lose the first ticket, 1/3 because we win the second, and 2/3 because we lose the third. And we can repeat this process so on. Okay, now we've got all the probabilities written out, and now they're just all written out in the form of multiplications of their individual events. Now we just have to multiply all these out and then add them up. Oops. The final probability of getting at least one winning ticket for the n equals 3 case is 19 over 27. And this is about 0.7 or 70%. There we have it. We've solved the case for n equals 3, and we found that if we buy 3 lottery tickets that each have a 1 out of 3 chance of winning, we have a 70% chance to get at least one winning ticket. And I don't think this 70% number would be obvious to anyone, but it does fall into our notion of what we were talking about before, where we said we're probably going to win. It's somewhere between that 51% and 99% range. Now, what would be nice to know is what are these probabilities of getting at least one winning ticket for different values of n? Right here we solved the n equals 3 case, but what about for n equals 10? Or 100, or a billion, or something like that? One of the nice things we had going for us for this n equals 3 case is that we could easily count all of the scenarios that could happen and then just compute the probabilities for each one and add them up. We just had to do these 8. But I think we could quickly see that for larger values of n, like 10 or 100, the number of cases we would have to calculate would just start growing huge really, really fast. What would be nice is if we just had like a single equation, some function that just takes in the value of n and then spits out what this probability is, so we could see how does this probability trend as the number of lottery tickets get larger and the probabilities of winning go down. To get this single nice equation we want, this function that just takes in our value of n and returns the probability of getting at least one winning ticket, we're going to revisit the n equals 3 case, but we're going to reframe things a little differently. First, let's just talk about the cases of winning exactly some amount of tickets. So for example, let's say that like P0 is the probability of getting 0 winning tickets, like 0 Ws. And let's say P1 is, the probability of getting 1 winning ticket, 1 win. P2 equals the probability of getting at least 2 winning tickets. And then P3 is the probability of getting 3 wins. One thing we can notice is that these are the only outcomes that can happen for n equals 3. If we have 3 lottery tickets, there's no way we can get, for example, 4 winning tickets, and there's no way we can get any less than 0, like we can't get -1 winning tickets. So all of these added together need to equal 100%, or 1.0. So we can say that 1 equals the probability of getting 0 winning tickets plus the probability of getting 1 plus the probability of getting 2 plus the probability of getting 3, and so on. The thing we're interested in, what's the probability we get at least one winning ticket? And the at least one winning part is right here, right? This is, getting 1 or 2 or 3. And what's nice is if we made this problem for a different value of n, for example, n equals 4, we could just, add another term here, right? P4 is the probability of getting 4 wins. And then if we did that, we just have another equation that looks like this: P0 plus P1 plus P2 plus P3 plus P4. And again, the probability of getting at least one winning ticket is all summed up in here, in these terms. And these are the terms where we had to compute all different possible ways of getting at least 1, of getting at least 2, of getting at least 3, and so on. But what's nice is we can just lump these all together in the sort of probability of at least 1. We could just say this is, P of at least 1. So if we rewrite this equation, for any value of n, we can write it as all possible outcomes, 100% probability, is equal to the probability of getting 0 tickets plus the probability of getting at least 1 ticket. And from there, we can just solve for this probability we want. We can just say that 1 minus the probability of getting 0 tickets is equal to the probability of getting at least 1 ticket. Now, regardless the value of n, all we have to do is figure out the case for winning or for getting 0 wins out of all the tickets we bought. And what's nice about this is there's only one way it can happen. It's not like how many ways are there we can win 1 or how many ways are there that we can win exactly 2. The only way we can get 0 wins is if all of them are losses. So for example, in the case of n equals 3, the
probability that we lose a ticket is just 2 out of 3, right? And since we had 3 tickets, it's 2 out of 3 times 2 out of 3 times 2 out of 3. Or another way to write this is just 2 out of 3 cubed. And for the case of n equals 4, it would just be 3 out of 4 chance of losing, 3 out of 4 chance of losing. Or another way to write it is just 3 out of 4 to the 4th. And in general, for any value of n, the probability of getting exactly 0 wins is just going to be n minus 1 over n, because the probability of winning is 1 over n. So like, for example, if n equals 10, you have a 1 out of chance of winning. Therefore, the probability of losing would be 10 minus 1, or a 9 out of 10 chance. This is the probability that we get a losing ticket raised to the power of the number of tickets we have. So in this case, just n. So the final formula would be, see if I run out of room here, 1 minus n minus 1 over n to the n. This equals the probability of getting at least one winning ticket for any value of n. Now that we have a nice formula, the next natural thing to do is just plot the values of f of n for different values of n. And of course, in the beginning, we get some simple, easy to compute numbers. For example, like n equals 1, it's just 100% chance you'll win, because by definition, the lottery ticket has a 100% chance of winning. For n equals 2, there's a 75% chance. For n equals 3, that was the case we solved earlier, it's around 70%. And so on, it'll just sort of have this kind of shape. And I plotted this in like a Python script, and then here I've just drawn it out. So what's really interesting is that it has this behavior of asymptotically approaching some value. And this value is around 63%. And again, there's nothing obvious about this 63% number, and there's also nothing obvious about this this asymptotic behavior as well. But it still falls within that notion we talked about earlier, where if we, for example, we're at n equals 100,000, so that means every lottery ticket has a 1 in 100,000 chance of winning, but we buy 100,000, we still are, probably going to get at least one winning ticket. We're going to get one winning ticket with around 63% chance. And that still follows that notion of probably, where it's some value, greater than 51%, some greater than 51%, but less than 100. Yeah, at this point, while this isn't obvious, I think this curve gives us a pretty good understanding of, if we're thinking about this 1 out of n problem for different values of n, what's the actual probability of getting one winning ticket? But it leaves us with this mystery of, well, what exactly is this number? And how do we calculate it? And the way we need to calculate it is find the value of the limit of f of n as n approaches infinity. So that is the limit as n approaches infinity of 1 minus n minus 1 over n to the power of n. So now, for the last part of this video, we're going to actually try and evaluate this limit and get a closed form solution for what this number, this 0.63, actually is. And just a quick disclaimer going into the last part of the video, evaluating this limit will require a bit more complicated math than we've been doing up until this point, as it will require some calculus. But with that disclaimer ahead, let's jump into the last part of the video and try to see if we can solve this. All right, let's start to work out this limit. The first thing we can do is just get rid of this 1 here. Basically, the complicated thing we need to figure out is right here, and we don't really have to worry about the 1. So not that these are equal, but really the only thing we actually care about is the limit as n goes to infinity of n minus 1 over n to the n, and then we can just tack on the 1 after. We knew from the plot before, we're expecting some number around 0.63. So the first thing we can always try to do is just plug in infinity and see if we get a number that makes sense. So if we plug in infinity, we basically get infinity over infinity, which is 1 to the power of infinity. So we kind of get something like this, and then this isn't really a determined answer, so we know we're not there yet. One interesting thing we can actually see from this limit is we could rewrite the this inner part a little bit. We can rewrite that as the limit as n goes to infinity of 1 minus 1 over n to the n. While this might not look like it's any easier to solve, it does kind of provide a little hint at what the answer might look at. You see, if we change this minus to a plus right here, this actually equals e by definition. And so for those who don't know, e is about, it's like 2.718, dot, 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 etc. So this is a well-defined definition for the value e, and this just kind of, gives us a little hint that, we might expect our answer to have some involvement with e in one way or another. One approach we can take with expressions like this that have an exponent is we can try to use logarithms to bring the exponent down. And just to remind everyone, if we, let's say for example, we're using the natural log, so we have a base of e. If we have, say, the natural log of some value x equals y, that by definition means that e to the y equals that value of x. And then if we substitute this top equation into the bottom one, we get something like this: e to the natural log of x equals x. And what this is basically saying is that if we have any value, like in this case we're just calling it x, but it can be anything, e raised to the power of the natural log of that thing just basically undoes itself and gives you back the original thing you started with. So what we can do is we can treat this thing like our x down here. So we can say that n minus 1 over n to the n, that should be the same thing as e to the natural log of n minus 1 over n to the n. And what's nice about this form is that now that we have a logarithm here, we can use the property of logarithms to bring this exponent out to the front. So now we have, this is the same as e to the n natural log of n minus 1 over n. Whoops, that kind of looks like a W. And this is the exact same thing as what we started with up here, this n minus 1 over n to the n. So now we can start trying to solve this limit. The limit as n goes to infinity of e to the n natural log of n minus 1 over n. And just like in our original limit, we discarded this one because it did, like, we can just add it on later. We don't really need to worry about this e either. All we need to do is figure out, what is this exponent going to be? And then we can just take e to whatever we solve for up here. So this is the same thing as saying e to the limit, e to the limit as n goes to infinity of n natural log of n minus 1 over n. So now we just need to figure out this value. Okay, so just a quick recap before we go further. This was the original limit we started with, and then we just discarded the 1 because the main thing that's difficult to figure out is this part of the expression right here, and then we can just take 1 minus our answer later. So we just really cared about this. Then we used logarithms and property of exponents to rewrite this term as e to the power of n times natural log of n minus 1 over n. And then we used the same reasoning as before, where we didn't really care about this 1. We don't really care about this e for solving the limit because all we really need to do is figure out what happens in the exponent, and then once we have the answer for this, we can just say that this is equal to e to the power of whatever that is. So we just drop the e. So now this is what we care about solving at this point. Now that we've done some manipulating of our original expression, we have a new form. Let's see if we can evaluate the limit now. I'm just going to rewrite it really quick. So the limit as n goes to infinity of n natural log of n minus 1 over n. If we plug in infinity, we get an infinity here times natural log of basically infinity over infinity, which is 1. And then we get a natural log base anything of 1 is just 0, so we basically get an infinity times 0, and this is just some indeterminate form, and we haven't really learned much, and we can't solve the limit yet, so there's still more work to do. Now that we've got another indeterminate answer, this infinity times 0, we need to try another approach, and one approach to try when you keep running into indeterminate answers like that, or like this, is to use something called L'Hopital's rule. L'Hopital's rule basically goes something like this. If you have the limit as, x approaches some value, let's just call it a, of the ratio of two functions, so let's just say it's like f of x over g of x, and you get something that's indeterminate, so maybe you get something that's like 0 over 0, or like 0 to the 0, or, like infinity to infinity, or something like that. One of these answers that just don't make any sense. What L'Hopital's rule says you can do is it says, okay, you got some indeterminate answer that's probably wrong. Just take the derivative of the numerator and denominator and then reevaluate the limit, and you might not get something that's indeterminate, and the thing you get should be correct. So you can just say the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. And all it says is that you might not get an indeterminate answer. So if you then get to this point and you say you get an answer of like 5, then you can just say you're done. The limit of f of x over g of x as x approaches a is just 5. And this doesn't guarantee that you avoid these indeterminate forms, but it says you can always try it. And then if you got another indeterminate form, you could just take the derivatives again and keep repeating this process until you finally got to some value that converges. Now, with that said, let's try to turn our expression into a fraction so we can try to take advantage of L'Hopital's rule. So if we have this expression, n times the natural log of n minus 1 over n, we can rewrite that as a fraction in the form of natural log of n minus 1 over n divided by 1 over n, because dividing by 1 over n, that's the same thing as multiplying by n, basically. So let's just try to evaluate this limit and see if this even does anything. The limit as we're now working with n approaches infinity, of natural log of n minus 1 over n divided by 1 over n. So we saw that before, that the natural log of n minus 1 over n, that just approaches 1 in the argument, so the whole thing just becomes 0. And then 1 over n as n approaches infinity, this is just going to tend to 0 as well. So now we get 0 over 0. We have some indeterminate form, and this is a good candidate to try L'Hopital's rule on. Let's now use L'Hopital's rule to evaluate our limit that's now in this fraction form. So for L'Hopital's rule, we need to compute the derivative of the numerator and denominator. So let's do the numerator first. So we need to compute the derivative of the natural log of n minus 1 over n. First, I'm just going to write down basically the general derivative for the natural log with some function in the argument. If we have some function of n, and we want to take the derivative with respect to n of natural log of, like, let's say some function inside u of n, that is equal to u prime of n over u of n. So in our case, u of n is going to be equal to n minus 1 over n. Okay, and now we need to compute the derivative of this n minus 1 over n. So before we compute the derivative, let's just rewrite this into a bit of a simpler form. This is just equal to 1 minus 1 over n. And then this is equal to 1 minus n to the power of negative 1. And so now if we want to take the derivative of this, we can just, the derivative of 1 is just 0. And using the power rule, this is just negative 1 over n squared. So this whole thing becomes 1 over, I'm going to put arrows. If we take the derivative dn of this, we get 1 over n squared. Because we bring the minus 1 in front, it cancels with that negative, and then we lower this by 1 to become negative 2, and that just becomes 1 over n squared. So this is our u of n, and our u, all we did was find the derivative of this, which is u prime of n, which we just said is 1 over n squared. So the derivative of our entire numerator term is just u prime of n divided by u of n, which is n minus 1 over n. So let's put these together over here. So the derivative on top, so 1 over n squared. Make that a little neater. N squared, all divided by n minus 1 over n. And this is the same thing as 1 over n squared times just the reciprocal of this. So n over n minus 1. And this all equals 1 over n times n minus 1, because this n will cancel with one of those. Okay, so now this is just the derivative of the numerator. So that's just for this term. Now we have to compute the derivative of the denominator, and we already saw what that was. We know that the denominator is the same thing as n to the negative 1, and then via the power rule, so if we take the derivative with respect to n, we'll just bring the negative 1 in front, and then reduce the power by 1 to negative 2, and this is the same thing as negative 1 over n squared. So now this is the derivative of our denominator. Okay, so now that we have the derivative of the numerator and the denominator, we can just evaluate the limit of those derivatives. So let's see if we can do that and then see if that actually converges. So we have the limit as n approaches infinity of, okay, the derivative of our numerator, which is this, 1 over n times n minus 1 over negative 1 over n squared. Oops. Try to write that a little neater. Okay, and just to make this a little neater, remember dividing by this term is the same as multiplying by the reciprocal. So we can say that this is the limit as n approaches infinity of 1 over n times n minus 1 times n squared over negative 1. So now this one of these n's will cancel with this, and we'll have the limit as n approaches infinity. And I'm just going to move this negative up here. Doesn't matter if it's numerator or denominator. Negative 1 over n minus 1. And whoops, we still have one n on the numerator, sorry. Okay, this looks good. So yeah, so now we can try evaluating the limit. So if we put infinity in here, we get negative infinity on the top and infinity on the bottom. And so those will just cancel and we'll get negative 1. All right, we're almost done here. So I just cleared some space, but we applied L'Hopital's rule, we found the derivatives, and we found out that this whole term converged to negative 1. Okay, so now that we have this negative 1, remember that this was really just us evaluating the limit in this exponent right here. So now that we know that this thing converges to negative 1, we really just have this as the limit as n goes to infinity of e to the negative 1. And there's no more n anymore, like this just equals e to the negative 1 or 1 over e. And then we still need to go one step further back to our original expression, because remember we dropped this minus 1 because it didn't matter. We really have now that this is equal to our 1 over e. So the final answer is going to be the limit as n goes to infinity of 1 minus n minus 1 over n to the n equals 1 minus 1 over e. And so I just turned around really quick and went on my computer and computed this. And yeah, I evaluated this 1 minus 1 over e. And just with some more precision, it became 0.632120.558 ... All right, so now that we got a final answer for our limit, let's go revisit the graph we were looking at earlier just to wrap everything up. And then just to remind everyone, so remember the y-axis was the probability of getting at least one winning lottery ticket in our 1 out of n problem, and then the x-axis was our value of n. And what we saw was that as n increased, which means we're talking about lottery tickets that have a lower chance of winning, but we're going to be buying more of them. As n increased, the probability of getting at least one winning ticket went down, but it asymptotically approached a single value, so it was never actually getting any lower than what we first looked at was about 0.63. And then when we actually did all the math and figured out what this number was, we found it was actually 1 minus 1 over e. This is just really unobvious and really cool. Again, like it still kind of lines up with our original notion that, we still probably get a winning ticket. It's more than 50% chance. But, who would have guessed that it's around 63%? And also, who would have guessed that it involves the number e? This is just a really nice, simple, yet very surprising answer to this problem. So if we buy, a million tickets with each ticket having a 1 out of a million chance, we're never going to have a probability that gets below this value. That's going to be it for the video today. I really want to thank everyone for watching, and I think this is just a really, really cool problem, because it starts off with something so simple, just, what's the probability we get a winning lottery ticket? And then it turns into just, all this cool math, and it ends up with this really nice, really unintuitive, like 1 out of E answer for the case of like buying infinitely many lottery tickets that all have basically a 0% chance of winning. Yeah, I just thought, this was a really cool problem, digging into it deeper. And again, thank you all for watching. I'll see you guys next time. Bye.